Welcome to the Financial Historian, where money, power, science, and history collide, and where the most important ideas in human history often begin as simple equations on paper. Today's story begins with one of the most famous formulas ever written, E equals mc. It looks simple. It's just three characters and a small exponent. But hidden inside that equation is a discovery that reshaped modern physics and eventually helped unlock the destructive power of the atomic bomb. When Albert Einstein introduced this formula in 1905, he wasn't trying to design a weapon. At the time, almost nobody imagined that the relationship between mass and energy could ever be used for anything practical. Einstein was trying to answer a much deeper question. How does the universe actually work? To understand how this equation eventually became connected to nuclear weapons, we need to go back to the early 20th century, a time when physics itself was facing a crisis. For centuries, scientists had relied on the laws of Isaac Newton to explain the universe. Newton's equations described motion, gravity, and energy with remarkable accuracy. Planets followed predictable paths. Objects behaved according to clear mathematical rules. The universe appeared orderly and understandable. But as scientists began studying atoms and light more closely, strange problems started appearing. Light sometimes behaved like a wave, but sometimes it acted like a particle. Electrons inside atoms moved in patterns that classical physics simply couldn't explain. The deeper scientists looked into matter, the stranger reality seemed to become. This was the scientific environment in which a young patent clerk named Albert Einstein began thinking about space, time, and energy. At the time, Einstein wasn't working at a prestigious university. He worked at the Swiss Patent Office in Bern, reviewing technical inventions during the day. But in his spare time, he was thinking about some of the deepest questions in physics. Then in 1905, Einstein published 4 scientific papers that would completely transform modern science. Physicists later called it his miracle year. One of those papers introduced a revolutionary idea. Mass and energy are not separate things. They are simply two different forms of the same physical reality. Einstein showed that a tiny amount of mass could theoretically be converted into a massive amount of energy. He expressed that relationship in one short formula, E equals mc squared. Energy equals mass multiplied by the speed of light squared. At first glance, the equation looks simple, but the number hidden inside it is enormous. The speed of light is about 300,000 kilometers per second. When you square that number, it becomes unimaginably large, which means even a very small amount of mass contains an extraordinary amount of energy. Nobody knew how to actually convert mass into energy in a practical way. Even Einstein himself never imagined that this idea would one day become the foundation of nuclear weapons. But over the next few decades, scientists continued studying the structure of atoms. And slowly, the hidden energy inside matter began to reveal itself. In 1911, physicist Ernest Rutherford made an extraordinary discovery. Through a series of experiments, he found that atoms contain a tiny, incredibly dense center called the nucleus. Almost all of the atom's mass was concentrated inside this microscopic core. Later, scientists discovered that the nucleus itself is made of particles called protons and neutrons, held together by extremely powerful forces. As researchers studied these particles, they realized something remarkable. The nucleus contained enormous amounts of energy locked inside its structure, but no one yet knew how to release it. That changed in 1938, when German chemists Otto Hahn and Fritz Strassmann conducted experiments with uranium, a heavy radioactive element. When they bombarded uranium atoms with neutrons, something unexpected happened. Instead of simply absorbing the neutron, the uranium nucleus sometimes split into 2 smaller nuclei. This process released additional neutrons and a surprising burst of energy. The phenomenon was later explained by physicist Lise Meitner, who had fled Nazi Germany because of her Jewish background. She realized that the uranium atom had undergone a process now known as nuclear fission. And suddenly, Einstein's equation was no longer just theoretical. When a heavy nucleus splits apart, the total mass of the resulting fragments is slightly smaller than the original mass. That missing mass does not disappear. According to Einstein's equation, it is converted directly into energy. In other words, a tiny portion of matter is literally transformed into pure energy. The implications were staggering. If scientists could trigger this reaction repeatedly, creating a chain reaction. Enormous amounts of energy could be released in an instant. But the timing of this discovery could not have been worse. By the late 1930s, Europe was sliding toward World War II. Nazi Germany was expanding across the continent, and many scientists feared that German researchers might also discover how to turn nuclear fission into a weapon. Several physicists who had escaped Europe, including Leo Szilard, became deeply concerned. They realized that a nuclear chain reaction might make it possible to build a bomb far more powerful than any weapon humanity had ever seen. But convincing governments to take this possibility seriously would require something powerful. It would require the name of the most famous scientist in the world, Albert Einstein. In 1939, physicist Leo Szilard visited Albert Einstein with an urgent request. Although Einstein was not directly working on nuclear experiments, his reputation carried enormous weight. Szilard believed that if Einstein warned the United States government about the potential of atomic weapons, they might take the threat seriously. Together, they drafted a letter to President Franklin D. Roosevelt. The letter explained that uranium might be used to create extremely powerful bombs, and that Germany could potentially develop them first. Einstein agreed to sign the letter. This document, now known as the Einstein-Szilard letter, helped trigger one of the most secret and ambitious scientific projects in history, the Manhattan Project. Beginning in 1942, the United States assembled thousands of scientists, engineers, and technicians to work on building an atomic bomb before Nazi Germany could do the same. Massive research facilities were built across the country. Cities like Los Alamos, Oak Ridge, and Hanford became centers of nuclear research. The scientific leader of the project was physicist J. Robert Oppenheimer, who gathered some of the greatest scientific minds of the era. Their challenge was immense. They needed to create a self-sustaining nuclear chain reaction. They needed to enrich uranium or produce plutonium. And they needed to design a device capable of triggering an explosion powerful enough to release the energy stored inside atomic nuclei. The key to the bomb was the chain reaction. When one uranium nucleus splits, it releases neutrons. Those neutrons strike other uranium atoms, causing them to split as well. Each new reaction releases more neutrons, which trigger even more fission events. Within fractions of a second, billions of atoms split apart. And with every split, a tiny amount of mass converts into energy, exactly as Einstein's equation predicted decades earlier. By 1945, the Manhattan Project had successfully developed two different atomic bomb designs. One was a uranium bomb called Little Boy. The other was a plutonium bomb called Fat Man. Before using these weapons in war, scientists needed to test whether the design would actually work. So they prepared the first nuclear test in history. On July 16, 1945, in the desert of New Mexico, the world witnessed the first nuclear explosion. The test was called Trinity. When the device detonated, a blinding flash illuminated the desert. A massive fireball rose into the sky, followed by a powerful shockwave that rolled across the landscape. In that moment, humanity entered the nuclear age. Physicist J. Robert Oppenheimer later recalled a line from the ancient Hindu text, "The Bhagavad Gita. Now I am become death, the destroyer of worlds." Just weeks later, atomic bombs were used in war. On August 6, 1945, the United States dropped the uranium bomb on the Japanese city of Hiroshima. 3 days later, a second bomb was dropped on Nagasaki. Both cities were devastated. Tens of thousands of people died instantly, and many more died later from injuries and radiation exposure. Shortly afterward, Japan surrendered, and World War II came to an end. But the world had permanently changed. For the first time in history, humanity possessed weapons capable of destroying entire cities in seconds. Ironically, Albert Einstein himself had almost no direct role in building the bomb. The U.S. government never granted him security clearance to work on the Manhattan Project. And when he later learned about the destruction of Hiroshima and Nagasaki, Einstein was deeply troubled. In later years, he admitted that if he had known Germany would fail to build an atomic bomb, he might never have signed the letter to President Roosevelt. Einstein's equation had revealed one of the deepest truths about the universe, that matter itself contains enormous amounts of hidden energy. But the decision to turn that knowledge into a weapon was not a scientific one. It was a political decision. Scientific discoveries reveal how nature works. But once knowledge exists, humanity must decide how to use it. The same physics that made atomic bombs possible also made nuclear power plants, medical radiation treatments, and many modern technologies possible. Einstein's equation did not build the atomic bomb, but it revealed the rule that made nuclear energy understandable. A small equation written on paper in 1905. 3 symbols. 1 idea and consequences that reshaped the course of world history. If you enjoy exploring the hidden connections between science, power, and history, make sure to subscribe. Because history doesn't just explain the past, it helps us understand the forces shaping the future.